Okay, so yesterday we were talking about chemicals. We said it's any substance that has a definite composition. We already had talked about like glucose. I think maybe about the end, that's where we were at when the bell rang in this class. Does anybody remember last year what the formula was for glucose? It had a C and an H and an O in it. I'll give you that hint. C, it was C6, H12O6. And then when we put two of those together, then you can make sucrose. This is what plants do to store the energy in a little more compact form. So sucrose, table sugar, is actually made up of two monosaccharides stuck together and then taking out a water molecule. We call it dehydration synthesis, if you remember that terminology from last year. Now, I would say most of you know the formula for water. What is it? The H2O. What is it for carbon dioxide? The name kind of gives you a hint.
Can I guess, is it CO2?
CO2, okay? So anything that has a definite composition like that is we're going to call a chemical. Okay, now, so here, think of these different things. Here's the formula for sucrose. If you add C6H12O6, you'd get C12, H24O12, but I said you take out a water for dehydration synthesis. So you take two hydrogens away and one oxygen, and you have the formula for sucrose. So here are the formulas for substances that have a definite composition. Like here's vanilla, the vanilla extract that you use for flavoring when you're making different kind of foods and stuff like that. Here is baking soda, that's sodium hydrogen carbonate. Like we saw in that video, the second burning one he had said it was sodium burning in chlorine gas, and it formed this molecule, this ionic compound right there. It's salt, NaCl, a real common substance. So when it comes to what we do in science, we said we have one of three categories it often fits into. Sometimes you can be doing more than one of these activities at a time. Basic research, you're just carrying it out for the sake of increasing knowledge. In other words, you don't have a problem you're trying to solve, you just want to learn more. I don't know, when we've talked about this before maybe 2 years ago, we may have talked about this same concept. And the example I like to use is, remember that movie about, I forget what his name is. Jane Goodall, maybe, I think it was Gorillas of the Mist or something like that. But she spent her whole lifetime studying the mountain gorilla in Africa. Not because the gorillas were endangered or anything like that, at least at the time she was doing her study. She just wanted to learn more and more and more about gorillas. Now, people can benefit from that information, but she was not trying to solve a problem. Like maybe today we might have a species that's becoming endangered and we don't want to know why. That wouldn't be this. This is just, you're just learning more for the sake of learning. Astronomers probably fit that category a lot, learning is everything they can about a certain star or everything they can about a planet. We're not trying to solve a problem, the planet's not is becoming extinct or anything like that, and we're trying to save it. We just want to know more about it. So that would be basic research. So what you're trying to do is you want to know how and why, for instance, like in chemistry, how does this chemical reaction take place? Why does it take place that way? What properties of this, does a substance have? If you kind of looked at some of those different things that he was demonstrating, putting different chemicals together, what properties did they have before and what properties were the new substances have after the reaction was finished. Sometimes these are like accidental discoveries. Now, most of you may not know what Teflon is, but you know about non-stick coating, like on, cookware. You have a frying pan that has that really slick surface on there, so if you fry an egg, you can just, it'll tip the pan sideways and it just slides right out. Well, Teflon was the first of the non-stick coatings that was discovered, but it was discovered by accident. The guy wasn't looking for Teflon. He was not looking for a non-stick coating. He was experimenting, reacting different chemicals to solve an entirely different problem. I don't remember anymore what it was, but what he did is, like chemists, they will pour their stuff out in the sink, and then at some point you have to do dishes. And when he did the dishes, he was feeling this stuff that he poured out in the sink, and man, he just found it extremely slippery in his hand. Like if you've ever had a wet bar of soap, you know how slippery that is? That's what it was like. And so his wheels start turning, thinking, what can we use? Because it'll reduce friction, so maybe we can coat things with that, and they will slide past each other, and we don't have to oil it anymore. It's just the two surfaces are just that slick that they'll slide over each other. Well, good scientists, always record everything they've done. Always writing it down. They never obliterate anything that they've written down. It just, if it didn't turn out, it just didn't turn out. No big deal, But because he had written it down, he knew exactly what chemicals he'd mixed together to make that. And that they end up developing the first nonstick coating that went on cookware. Later on, they would put it like on saws. Like if you're sawing a piece of wood, it's you can have a lot of friction when you're cutting the piece of wood. Well, if you coat the saw with nonstick coating or like Teflon, it slides. Have any of you helped with plumbing? You ever heard that Teflon tape? That white tape that they wrap around the joint so that you can cinch up the two pieces really tight? But it was just discovered by accident. The guy wasn't looking for nonstick coating or anything. It was just an accident. But being able to recognize that you have discovered something of value is kind of important. Now, applied research is generally carried out to solve a problem. Like we need to, they're going to often take information that was learned in research and apply it to a problem. Let's say, give you an example of this. During World War II, there were some researchers that were trying to figure out a better way of communicating, like between ships and airplanes during bad weather. That was their biggest trouble, is being able to communicate when the conditions were bad. And they discovered that they could communicate much more in bad weather without it being affected by the bad weather if they used microwaves. So that's why the guy was researching microwaves. How do you communicate with that? And he discovered one day that, if you remember back in physical science, I think we talked about this. He had in his lab coat, and his favorite snack was a Hershey's candy bar. He had in his pocket. Well, on the day that he was working with this microwave, he took his candy bar out of his pocket, and it was all soft and mushy, And, good scientists thinking, now, what's different about today than ever before? My candy bars have never been all soft like this before. And then he experimented with putting his his Hershey's candy bar in front of the microwave beam and discovered, he could heat up things with the microwave. Okay, so he was doing just basically basic research. He wasn't trying to figure out how to cook meals or anything like that. Well, when they went to the moon, we had to figure out a way for these astronauts to heat up their food to eat. So applied research took what he had discovered about microwaves and figured out a way they could actually basically put a microwave on the spaceships to be able to heat their food while they're out in space. So that would be applied research. Okay, your development, they developed like a microwave to cook food, or developing new refrigerants. We discovered, for instance, that the early like Freon and stuff like that actually damaged the ozone in our ozone layer. So we had to come up with new refrigerants that would also cool, but wouldn't end up harming the ozone layer. So that would be an example of applied research. What other refrigerants can we come up with that will do the same thing without having a bad side effect? Okay, now technological development is, it involves the production and use of products that improve our quality of life. So, once they had made microwaves to use on spacecraft, then why don't we have microwaves, in the homes and restaurants? Some of the first microwaves were, I've seen pictures of them. They look like they're about this square, stand up about this high, and they had them in restaurants, after they prepared the food, and before the food would go out to the people they were serving, they just pop it in the microwave a little bit. So they had restaurant microwaves at first, and then they were big. But then, why not everybody have a microwave at home? An interesting thing about microwaves is that we had this microwave. Believe it or not, we bought it at J.C. Penney's. Back then, Penney's sold all kinds of stuff. I even had in our married life, I've had a pair of snow tires that was sold by Penney's. They actually had kind of like a standalone building at Penney's that would install tires and batteries and do all that kind of stuff like that. But they also sold small appliances, and so our first digital microwave, not the one with the knob, but where you could actually punch in a number, was a J.C. Penney microwave, and we had it for a long time. It always worked great. And we went to, I think it was Topeka, to a museum where they had, different, it wouldn't be Natural History Museum, but where they, things that people used in the past, and we found our model of the microwave in the museum. And the kids still to this day, they say, we had this old microwave that they actually could have gone to the museum, but it was a good one. Computers, first computers were really, the first computers were used in the military to calculate how far, if they fire, like artillery, if they're going to hit a target, at what angle do I need to fire it at so I can hit my target, and what angle and stuff like that. They use the computer to calculate all these tables of launch angles and stuff like that. Well, then big companies would have computers. Like IBM is one of those that had big, what we call mainframe computers. You and I, have these little laptops like this, which like this laptop. Well, actually, here's to give you an idea about the computing power. Your calculator is a more powerful computer than the computers they used on the Apollo missions to go to the moon. So they're pretty crude computers, but man, they work good. I mean, imagine just thinking, leaving the Earth and going to another object out in space and coming back again, and it's all controlled by a computer that was crude by today's standards, but it worked. That's all it has to do is work. And the beauty of computers, they can do something over and over and over again and not get tired. Catalytic converters on car, we discovered that certain chemicals, certain metals could make exhaust coming out of a car that was polluting, and we could change it into chemicals that aren't as polluting. So today, almost every car, I think every car has catalytic converters, most pickups do, probably not diesel trucks, but, or biodegradable materials, making things out of materials like these packing peanuts. There's a lot of them are made out of, I think they're made out of starch, some of them. Actually, some of those packing peanuts, if you put them in your mouth, they'll actually dissolve in your saliva because they're just made out of starch. But that would be biodegradable, so it doesn't end up stacking up on the ground. It actually goes away eventually. So basic research, applied research, technological development often overlap. One is kind of blends often into the other. You will have some questions on your assignment that where they'll ask you, or they'll say something that they're doing something, and you have to pick, which area does it belong to, and you might find some of them that belong to more than one area. Okay, that's it for today.